Hello everyone, welcome to part 3 of the probability distribution video series. So in this particular tutorial, we are going to talk about normal distribution. This is probably the most widely used distribution in the whole world, and I'm going to try and cover everything that you require to know about this distribution. So let's dive in. First of all, let's look at this curve. This is a curve representing the heights of the Indian adult males. So 70 is around the average height of the Indian adult males. As you can see, most of the adult males seem to be revolving around 70 inches. The guys who are very tall are very low in number. That's why their density is low right here. And the guys who are very short are also very low in number. They are also very low, I mean, because the density here is also very low. So this is actually how the normal phenomenon goes in the real world. You can also take their weights and they will probably look very similar. So most of the people will be somewhere around normal average height, and there will be a few obese people, and there will be a few people who are very lanky and thin. So this is how the normal distribution curve looks like. Let's talk about the mean and standard deviation of the distribution first. This is the mean, 70. Here, the standard deviation sigma is 2 because 70, then 72, then 74. So as you can see, within the range of one standard deviation away, the probability is 68%. That means 68% of the people, 68% of Indian males are covered within this range. If we now take 3 standard deviation to the right and to the left, 99.7% of the people of the Indian males should be covered according to the normal distribution. So how does the probability density function of or PDF of the distribution look like? So it looks hideous, but let me break this down for you. So sigma is the standard deviation. So for this distribution, it is 2. Mu is the mean. So the mean here is 70. And x is basically the random variable. So if you want to know the probability, I mean, obviously it's a continuous distribution, so we cannot detect the probability directly. Rather, let's assume that if you want to detect the likelihood or density of some person having a height of say 74 inches, then you can just plug in 74 right here in place of x. You can plug in 70 as nu and 2 as sigma, and then it is going to give you the density or likelihood of that Indian male being a height of 74 inches. So the mean and expected value you can calculate using our standard formula, which is the integration between minus infinity to plus infinity x fx dx. And if you do the integration of this hideous formula, you are going to get nu. So as I was saying that this nu is the mean. So I was saying that before without any proof. So now this is the proof that indeed nu is actually the standard mean or the expected value of this particular PDF. Similarly, if you take the variance, if you do the math, if you calculate ex square and ex whole square and subtract them, then you are going to get sigma square. And we know that the square root of the variance is called the standard deviation. So sigma is the standard variation. So I have also proven that sigma is indeed the standard deviation of this particular PDF. Let's talk about standardization of normal curve. So this is a normal curve where nu is the mean and sigma is the standard deviation. We can transform this curve into this curve where 0 is the mean and 1 is the standard deviation. But how are we going to do that? So let's go back to the previous example of Indian male adults and their heights. So in order to transform those heights to the standardized normal distribution, we have to first take the mean and standard deviation of all the heights, which we showed before. Mean was 70 and the standard deviation was 2. Then we will have to perform the z-score normalization of all the heights using this formula. So if some Indian male has a height of 74 inches, so you are simply going to do 74 minus 70 divided by, and that will give you the z-score of that particular Indian adult male. So if that particular normal curve were actually formed based on 100 Indian adult males, so we can actually perform the Z-score normalization on all those 100 heights. So x1 minus nu by sigma, x2 minus nu by sigma up until x100 minus nu by sigma. So we are going to get from Z1 to Z100. So these Z1, Z2 up until Z100 will follow a normal distribution where the mean is 0 and the standard deviation is 1. So that is how we can convert very easily an n new sigma distribution to an n 0, 1 distribution. Now, why is this important? So let's see. As we already said, since normal distribution is a continuous distribution, we mostly care about a range of value. So if we want to get the probability, we have to get the probability of a range of x values, right? So for example, we can ask the question, what is the probability of Indian adult males having a height of 70 to 75 inches? Or we can say, what is the probability of an Indian adult male to have height less than or equal to 72 inches? That kind of range query for probability is valid for continuous cases. So there are two ways to get such query values. One way is to do simple integration from minus infinity to 72 in this case for the function fx. And this is the more difficult way. The easier way is to simply use the z table. And the z tables are given for the standard n01 cases. Now, since normal distributions are so widely used, that is why people tend to use the z-table, and there are actually z-tables available. Now, in this whole series, I'm probably going to cover like 15 different distributions, and these z-tables will be available only for maybe two or three of them, which are the most important ones. So now let's see how exactly can we use the z-table to get this kind of cumulative distribution function value. So let's look at this sample table. This is not the full table. This is a partial table just for your understanding. For example, this value right here is 0.5040. What this means is probability of z less than equal 0.01 is equal to 0.5040. Again, let's look at this. Probability of z less than equal 0.43, 0.4 and 0.43 is equal to 0.6664. So the integration result of probability of c less than equal 0.43 is going to be 0.6664. That is how very easily we can get the CDF or the cumulative distribution function. This is very similar. This is just for the negative cases and it is the same thing. So probability of c less than equal minus zero point 0.1 is equal to 0.4602. So let's see an example of how we can use this table. So what is the probability of an Indian male having height more than 71 inches? So our mean height was 70 inches, standard deviation was 2 inches, and we need to estimate what is the probability of x greater than or equal to 71. So the z-score here, we have to first calculate the z-score. The z-score for the height 71 inches is 71 minus nu, the mean is 70, divided by standard deviation, which is zero point 0.5. Now we have to look up the score of zero point 0.5. So probability of z less than equal 0.5 is equal to 0.6915. So which is cool. We can just get it from the table. Now what was our question? Before we look at our question, let's graphically see what this looks like. So this looks like this. So this is the 0 0.5 and this is the 0 0.5 vertical line. So probability of z less than equal 0.5 means the entire area to the left of this particular vertical line. And this area is 0.6915. But was this the question? No, the question was actually probability of x greater than 71 because we were trying to see the probability of an Indian male having height more than 71 inches, right? So x greater than 71 and this is the same as saying probability of z greater than zero point 0.5 because 71 was converted to 0 0.5. Now what did we actually calculate from this table? We calculated probability of z less than equal 0 0.5. So in the complementary rule, we know that probability of c greater than 0 0.5 is actually the same as 1 minus probability of c less than equal 0 0.5. That means this particular area and it becomes 0.3085. So this is how easy it is to actually solve this kind of problems from the z table. Let's now talk about central limit theorem, which is one of the core principles revolving around the normal distribution. So this is a normal curve. We saw this before. Now, what is random sampling? So let's try to understand random sampling. So if we randomly sample some heights from this distribution, most of the heights will come from this particular place. So around the 70 inches, because the maximum amount of density is around 70 inches. And only very few samples will come from these areas which have much lower density. So that is random sampling for you. So in random sampling, we are going to get most of the samples from areas with high density and very low amount of samples from areas with lower density. So let's now discuss the central limit theorem with an example, because I think the example is the best way to actually understand this theorem. So let's say we have this nice uniform distribution, which we actually talked about in one or two tutorials away in the uniform distribution tutorial. So here we can see that we have the six possible outcomes. So obviously, if you are rolling a dice has six sides, and you can think of these values as those sides. So side 1, side 2, side 3 up until side 6. And if we assume that the dice is uniformly distributed, or the dice has like uniform phases, then each of these outcomes are equally likely. So probability of having phase 1 is 1 by 6, probability of having phase 2 is 1 by 6, and so on and so forth. So if we now randomly sample, if we perform random sampling on this particular distribution, we are going to obviously get almost equal number of ones, twos, threes, fours, fives, and sixes, right? Almost. I mean, obviously, it will not be exactly equal, but it will almost be equal. So first of all, let's do one thing. Let's sample from this distribution 50 times. That means maybe we are going to have five threes, maybe eight fives, and so on and so forth. So basically, we are going to take 50 of these, and we are going to take their mean, which we call new one. Let's again do the same thing. Let's again sample from this distribution 50 times and take mean new 2. Now we can do this 1000 times. We can do this sampling from this distribution 50 times, calculating the new one, calculating new two. We can calculate up until new 1000, right? We can actually repeat this process 1000 times. So in this way, we can get 1000 means. Now, the interesting thing is this 1000 means will follow a normal distribution. This is very incredible because the original distribution from which we were sampling these values from are not normal, rather they are uniform distribution. The moral of the story is if you actually follow this procedure from any distribution, it can be Poisson distribution, uniform distribution, maybe exponential distribution, or whatever. If you take those means and if you actually try to estimate a PDF or a density function from all these means, you are going to get a normal distribution. So this is the core of the central limit theorem. So there are some prerequisites for this to happen. First of all, as I said before, these sampling and collection of means can be done from any probability distribution, but the only condition is they will have to have finite mean and variance. And this is true for almost all distributions, so we don't have to worry much about this. The next thing is when we are doing the random sampling, they have to be performed in an IID manner. So what is IID? IID means independent and identically distributed. So what does independent and identically distributed mean? So independent means suppose we roll the dice first time. When we roll it again, the outcome of the second roll does not depend on the first roll. So each trial is independent. And what does identical mean? Identical means all the dice roll outcomes, all our trials are being sampled from the exact same uniform distribution. It doesn't have to be uniform, it can be any other distribution, but the distribution has to be constant. So you cannot change the distribution and then cannot perform sampling. That is not possible. If you do that, then the central limit theorem will not be effective. So that is all about the normal distribution. Hope you like the video. If you like it, please feel free to subscribe and share. And there is a donation link in the description, so you can donate to our channel and support our content. Thank you very much.